Greetings, physics students. Mr. Resentis again. I'm still on chapter 9 and we're still talking about heat. Following along, you'll turn to page 305 in your book. Now, before we address heat, let's remind ourselves what temperature and internal energy is. Temperature is just a measure of kinetic energy. And kinetic energy, of course, is the energy of motion. Internal energy is the sum total of the energies in a substance. And so we're going to now start talking about internal energy as delta U. And now it's because it's change in internal energy. And see, things can be added to or taken away from this system. And perhaps in chemistry you remember talking about this very subject, and energy was I think Q is what it was called. There's a change in Q, but you still used U. And so we haven't changed that. We're just talking about the flow of energy from one system to another system, and that is what heat is. Heat is the energy transfer between two substances. All right. Now we measure that using temperature because it's going to be a measure of the kinetic energy. So you could think of it this way: that heat is energy in transit. So heat doesn't flow. Heat doesn't flow from the fire to the pot to the hand. Energy flows, and we describe the heat as that transfer of energy. So we have to be very specific about the vocabulary that we use, because that could cause us problems with multiple choice questions. So the units for heat, the SI units for heat, SI units for the System International units for heat are joules. All right? Those are the units for heat. So heat can do work, and we'll talk more about that later. Now, a calorie is 4.186 joules. Now, that's small. That's a small c. A large c is a dietary calorie, and that's a kilojoule. But we're getting a bit off topic now. But when we look on food packages and we see calorie, it's a capital C, and they use a kilocalorie. But we use calories, which is a small c. Let's move on. What are some ways that energy can be added or taken away from a system? How can heat be? How can the heat of a system change? Well, the heat of a system could change by fire, as you can see in this image. But heat of a system can also change by friction, by stretching, or by impact. So if I have, for example, if I have a hammer, let's say I have a hammer, and I strike a nail, which is in wood. If I have a hammer and I strike a nail in wood, we can add energy to the system by friction. I'm hitting it. We can also by deforming it, by stretching it as a result of the impact. So that I'm going to add to or take away energy in this system by making contact with it through friction, stretching, impact, etc. So there's some ways that we could add some energy to a system other than just using fire, which is, of course, the most obvious way. All right? So the sum changes in potential, kinetic, and internal energy is equal to 0. Alright, so remember, delta just means change. Change in potential energy plus change in kinetic energy plus change in the internal energy equals 0. So if you recall, potential energy is AL, potential energy, equals the mass times gravity times height. Let's see, kinetic energy, if you recall, I-N-E-T-I-C, energy, equals 1/2 mass times velocity squared. And kinetic energy is, we measure that using temperature. Kinetic energy is the motion of the particles. Kinetic energy is here, and then potential energy is measured in work, really, the work done on a system. And so that's why you're seeing this, you're revisiting these concepts that we already talked about before, with like conservation of energy. So if we rearrange this equation, potential energy final minus potential energy initial plus kinetic energy final minus kinetic energy initial plus the change in U, that all of that could because that's basically what change in potential energy is. That's change in kinetic energy. And we rearrange this further, we could get U by itself to find the internal energy, which is delta U. As I mentioned before, delta U is internal energy. We could say that the potential energy final plus the potential energy initial minus the kinetic energy final plus kinetic energy initial. All right, and so if, remember, these could be 0 and dropped out and made this a lot simpler. So let's try a practice problem. Here's practice problem B on page 311. Let's take a look at this practice problem and see if we can apply this equation. All right. So a worker drives a spike, and so we have the mass of the spike equals 0.500 kilograms. So we have a worker drives a spike into a rail tie using 2.5 kilograms. So we have the mass of the hammer equals 2.5 kilograms. That's an H there. The velocity of the hammer, so we have the veloc of the hammer equals 65.0, and that's velocity, so it's meters per second. Is now 1/3 of the hammer's kinetic energy is converted to internal energy of the hammer and the spike. How much does the total internal energy increase? Well, we said that delta U equals the, not all of it, but just 1/3 the kinetic energy of the hammer. That's H. All right, so 1/3, 1/2. We already said that kinetic energy is 1/2 mass times velocity squared. So 1/2 the mass of the hammer times velocity of the hammer squared, right? So we could say 1/6 2.5 kilograms times 65.0 meters per second. So here's our mass and here's our velocity, and all I did was simplify. And so we have delta U equals 1.76 3 sig figs times 10 to the third. And remember, the units are joules. All right? So potential energy is 0. We don't have potential energy is playing a role in this example. So let's try another one. Practice problem B. This is number 3, and again I'm on page 311. a 3.0 times 10 to the negative third, that's to the negative third, kilogram copper penny falls 50 meters. So we know that the mass equals 3.0 times 10 to the negative third kilogram, and we know that the height equals 50.0 meters. 65% of the initial potential energy goes into increasing the internal energy of the penny. Determine the magnitude of that increase. So delta U equals not all of it, just 65%. So we're going to have to say that it's 0.65, that's 65% of the potential energy initial, and that should work. I mean, that's all we need. So let's have a look here. So it would be 0.65 times the potential energy. We already said that the potential energy equals the mass times the 9.81. That's the acceleration, meters per second squared, times the height, which is 50, and that's where the potential energy comes from the height. And so if we multiply those, we get 0.96 joules. All right, it's only 65% of the potential energy. All right. So let's try one more. This is the section review. I'm no longer on practice problems. I'm jumping down to section review because these are all very similar and so we're just practicing a very similar problem. Niagara Falls. If 505 kilograms of water falls a distance of 50 meters, so we have the mass of the water equals 505 kilograms. We have the height of the water, which equals 50 meters. So in this situation, we're going to use potential energy here, it looks like. What is the increase in internal energy of the water at the bottom of the falls? Now assume that the final kinetic energy is 0. And so we know that it's going to continue to move, but let's just assume that it comes down and comes to a complete stop. So the change in U equals mass times gravity times height, just as we did up here. However, we only did 65% up here. We want to know all of it here. So it's just mass is 505 times 9.81 times 50. I apologize, there's no units here, but this is kilograms, this is meters per second squared, and this is meters. And we multiply those, we'll get 2.5 times 10 to the 5th joules, right? 2 sig figs. Well, my apologies, I should probably bring this to 3 sig figs. I only brought it to 2. That's my error. I think it's 2.4 something, but that's close to the answer. Proper answer would have 3 sig figs. My apologies.